Welcome to the lecture titled Identification of Second Order plus Date Time Model with Pole Multiplicity. Earlier, we have derived a set of analytical expressions for identifying parameters of the second order plus date time transfer function models. But we have certain limitations, as we have discussed earlier. When there will be pole multiplicity, one has to take care of the analytical expressions. In this lecture, we shall discuss how the same set of analytical expressions can be used to identify transfer function models with pole multiplicity. We shall see how we can identify a model transfer function of the form G s is equal to k e to the power minus theta s upon T 1 s plus 1 square. This type of model is known as models with pole multiplicity. Now, before going to that, I would like to repeat certain things we have already discussed in our last lectures. The set of analytical expressions we have derived for identifying the second order plus date time transfer function models. Now, the relay feedback system is arranged in this fashion. When the relay test is conducted, at that time the reference input is set to 0. And we have also assumed earlier the transfer function model that are identified to be of the form G s is equal to k times plus minus T 0 s plus 1 e to the power minus theta s upon T 1 s plus minus 1 times T 2 s plus 1. Now, the G s is the dynamics of the actual system, which model transfer function model is to be identified. Now, what we have done earlier to design a set of to derive a set of analytical expressions, we had to express the transfer function model in state space form, where we got the state equation of the form x dot t is equal to a x t plus b u t minus theta. So, we assume that the delay is there in the input. Therefore, this G s in equation number 1 can also be written in the form of y s upon u s e to the power minus theta s is equal to k then plus minus T 0 s plus 1 upon T 1 s plus minus 1 times T 2 s plus 1. So, this is how we have formed or got the state equation given in equation number 2. Similarly, the output equation is expressed as y t is equal to c x t. Now, the a, b, c constants of the state and output equations are given as a in diagonal form as lambda 1 0 0 lambda 2 and b as 1 1 and c as k lambda 1 lambda 2 lambda 1 plus lambda 2 upon lambda 3 times lambda 1 minus lambda 2 and minus k lambda 1 lambda 2 times lambda 2 plus lambda 3 upon lambda 3 lambda 1 minus lambda 2, where lambda 1 is equal to minus plus 1 upon T 1 and lambda 2 is equal to minus 1 upon T 2 minus 1 upon T 2, and that of the lambda 3 is given as lambda 3 is equal to plus minus 1 upon T 0. Now, it is evident from equation from the constant c that when lambda 1 is equal to lambda 2, we cannot get the state space representation correctly, or indirectly speaking. Now, this state space equation can be used when lambda 1 is not equal to lambda 2. With that condition, we started our analysis and we found a set of analytical expressions using the output waveform. So, what is that output waveform we got? This is the type of limit cycle output we got when the relay test was conducted. So, the relay test resulted in some typical output waveform of this form, whereas the input to the system relay output is given in the rectangular signal form. Now, this output signal has got some critical points like the zero crossings, and peak amplitude and the negative peak amplitude or the valley amplitude. So, that way we identify these 4 points and derive analytical expressions for these 4 points, resulting in 4 general expressions. Those are given by equation number 17, equation number 18 and equation number 31 and equation number 28 perhaps. I have missed the expression for AP. So, AP also will get in the form of K, then H1 plus H2 and so on. So, basically what we have done so far, that using the output waveform, some critical points of the output waveform, we have been able to derive 4 analytical expressions corresponding to the peak amplitude AP, this is the peak amplitude, and similarly the negative peak AV and the first zero crossing occurring at time t0 t0. So, assuming that y t0 equal to 0 and y t2 is equal to 0. So, these 4 outputs or 4 points of the output signal results in 4 analytical expressions. Now, those analytical expressions can be used to estimate the parameters of the second order plus date time transfer function models, like the steady state gain T0, T1, T2 and theta, provided lambda 1 is not equal to lambda 2. This point is to be taken care of. When lambda 1 is equal to lambda 2, at that time the dynamic model will have pole multiplicity. I mean to say, these expressions, analytical expressions are valid provided lambda 1 is not equal to lambda 2. So, this is correct, true provided lambda 1 is not equal to lambda 2. Similarly, the expression AB is also correct or applicable for the case that lambda 1 is not equal to lambda 2. Now, when lambda 1 equal to lambda 2, what happens to the state space equation? Can we obtain the state space representation in the same form with little changes? That we shall discuss in this lecture. I will begin with the relay control system, where the relay will be subjected, or the relay will be experiencing a dynamic system with pole multiplicity. Let us assume that Gs is equal to k e to the power minus theta s upon T1 s plus 1 times T1 s plus 1. So, I can write Gs h k e to the power minus theta s upon T1 s plus 1 square. This is what we mean by pole multiplicity. We can have more number of poles also. Let us begin with the simplest case, where the system dynamics is assumed to have got 2 identical poles located at the same place of the S plane. Now, in this case also we can find the dynamic equations for identification of transfer function model parameters. So, in this transfer function has got how many unknowns now? We have got 4 unknowns: the steady state gain k, the time delay theta, the time constant T1 and the time constant T1. So, as evident from this one, in place of 4 unknowns, actually how many unknowns we have? K, theta and T1. So, there are basically 3 unknowns associated with this second order plus date time transfer function model with pole multiplicity. So, we need to derive 3 analytical expressions that can be used to identify the model parameters. Now, where to repeat all those things and find 3 analytical expressions? If it is possible to use the previous earlier derived general expressions, then our life will be easy. Where to go for further analysis of this typical model? Then effort will be made now to show that the state space representation of this second order plus date time model with pole multiplicity can be given by equation number 2. I mean, can we get the same sort of state space representation for the model with pole multiplicity. That we will verify now. I will begin with the second order plus date time transfer function model with pole multiplicity, where there will be two poles located at the same locations. Now, let G s be given by the steady state gain k e to the power minus theta s upon T 1 s plus 1 square. Now, I can write this G s in the form of y s upon, since G s is equal to y s upon u s, it is not difficult to write y s upon u s times e to the power minus theta s h k T 1 s plus 1 square, okay, because our input to the plant is assumed to be delayed inputs when the plant is subjected to relay test. Therefore, please allow me to write y s upon u s e to the power minus theta s h k upon T 1 s plus 1 square. Now, this can be further simplified in the form of k T 1 square s plus 1 upon T 1 square, which again let lambda is equal to 1 upon T 1 implies y s upon u s e to the power minus theta s is equal to k lambda square upon s minus lambda square. So, this again can be expressed as y s upon u s e to the power minus theta s is equal to k lambda minus alpha upon s minus lambda s minus lambda minus alpha. So, what I have done here, I have introduced a small number where the small number lambda tends to 0. When lambda tends to 0, I have basically got the same expression. So, y s upon u s times e to the power minus theta s becomes k lambda square upon s minus lambda square when alpha tends to 0. So, always it is possible to write this expression in this form provided alpha tends to 0. Why I have done so? We will see. The effort is to bring this state space representation of this dynamics in the standard form that we have obtained earlier for the second order general second order plus date time model case. Then it is possible to further express this expression in the form of k lambda minus alpha by alpha times alpha by s minus lambda times s minus lambda plus lambda. Okay. Then next what I will do, I will write this in the partial fraction expansion form. Now, this same expression now y s upon u s e to the power minus theta s, which is given as k lambda minus alpha upon alpha upon s minus lambda plus alpha, when expressed in the partial fraction expansion form gives us k lambda minus alpha upon alpha 1 upon s minus lambda minus 1 upon s minus lambda plus alpha. Please keep in mind that alpha tends to 0, only then we are getting the same expressions that we that our analysis begin with. Then this expression further can be written in the form of k lambda minus alpha by alpha times 1 minus 1 with 1 upon s minus lambda 0 1 upon s minus lambda plus alpha times 1 1. So, basically what I have been doing, I am trying to find the same dynamic model using the state space equation constants. So, what is the state space equation constant? If you look minutely observe this one, what I have tried to do, I am trying to get the same transfer function model using the equation C S I minus A inverse B. So, we know that for linear time invariant system, we have the transfer function model to state space conversion and state space model to transfer function model conversion with the help of the standard equation given by C times S I minus A inverse B, where C, A and B are the constants of the state equation. In that case, upon comparison we get that the same transfer function model can be obtained using the constant C, A and B, where C is equal to now k lambda minus alpha upon alpha times 1 minus 1. It is of dimension 1 into 2. Now, similarly, A is now obtained as lambda 0 and 0 lambda minus alpha, and B is obviously are 1 1. Thus, we have got a state space representation of the dynamic second order plus dead time model with pole multiplicity, where there are two poles given by a state equation, where the state equation is now x dot t is equal to A x t plus B u t and u t minus theta y t is equal to C x t, where A is found to be lambda 0 0 lambda minus alpha, B is 1 1, whereas C is given as k lambda minus alpha upon alpha times 1 minus 1. Allow me to write the C in some other form now. Other means I will simplify the C now. Now, C can also be extended to the form of k lambda minus alpha by alpha minus k lambda minus alpha by alpha. Again this can be written as k lambda minus alpha by lambda minus alpha in the denominator minus k lambda minus alpha by lambda minus alpha. So, why we are doing so? We are trying to get the state equation represented in the original form. What is that original form? We have got the system state equation represented by this form, where x dot t equal to A x t plus B u t minus theta, y t equal to C x t, have got A, B, C given in this form. Now, basically I have been able to obtain this standard form using analysis. When that is possible? That is possible provided I assume that when lambda 1 equal to lambda and lambda 2 becomes lambda minus alpha, then whatever A, B, C we have got, then A becomes lambda 1 0 0 lambda 2, B equal to 1 1, and obviously C will be now in the standard form of k lambda 1 lambda 2 lambda 1 plus lambda 3 by lambda 3 lambda 1 minus lambda 2 minus k lambda 1 lambda 2 plus lambda 3 by lambda 3, lambda 1 minus lambda 2. This is the standard form. So, we can obtain the same A B C, or we can express this A in the standard form with the assumption of lambda 1 equal to lambda and lambda 2 is equal to lambda minus alpha, and B no changes. Already we have got the B in the specified form. Now, what about the C? C is available in this form. I am arranging it a little bit, where I am substituting lambda by lambda 1 and lambda minus alpha by lambda 2. Therefore, I get a term as lambda 1 minus lambda 2 in the denominator, but we have got additional terms also in the general expression for the C. Therefore, with the assumption, further assumption of when lambda 3 tends to a large number, infinity, in that case, then what C becomes? C becomes when lambda 3 tends to infinity, then I will get this in the form of k lambda 1 lambda 2 upon lambda 1 minus lambda 2 times 1 upon lambda 1 upon lambda 3 plus 1, and the second term will be similarly k minus k lambda 1 lambda 2 and lambda 1 minus lambda 2 in the denominator with lambda 2 by lambda 3 plus 1, and as we have assumed that lambda 3 tends to 0, therefore, this will be 0 and similarly this will be 0. So, we are multiplying this factor by 1 only, resulting in the expression for the C as k lambda 1 lambda 2 upon lambda 1 minus lambda 2 minus k lambda 1 lambda 2 upon lambda 1 minus lambda 2. Okay. So, finally, the reason for doing all these analysis is that with proper assumptions, simple assumptions or introduction of the terms, that when lambda 1 equal to lambda, when lambda 2 equal to lambda minus alpha, with the constraint that alpha tends to 0, alpha tends to 0, at that time it is possible to find the transfer function model as a transfer function model with pole multiplicity. We are dealing with a second order plus date time delayed transfer function model, and where we have got a 2-dimensional A, B and C. Okay. So, ultimately this same setup, I mean this general expression can also be obtained in the form of this G s can be expressed in the form of a transfer function model with pole multiplicity k e to the power minus theta s upon T 1 s plus 1 square, when lambda 1 is equal to, already we have got lambda 1, lambda 2 and lambda 3. Keep in mind, when lambda 1 equal to lambda, lambda 2 is equal to lambda minus alpha, where again alpha tends to 0. Please keep in mind, alpha tends to 0, then only you will get the dynamic model in the form of model with pole multiplicity. Okay. Again, to obtain this second order plus date time transfer function model, we have to assume model with no 0 particularly. We have to assume that lambda 3 tends to a large number. So, if you allow me to make these assumptions, then all the analytical expressions we have derived so far can be extended to identify the transfer function model parameters of this model with pole multiplicity, because one has to properly substitute the lambda values, the lambda 1, lambda 2 and lambda 3, then the same set of analytical expressions as I have said or shown earlier. What are those analytical expressions we have obtained? These are the analytical expressions. Now, these analytical expressions are not valid or cannot be used when lambda 1 is equal to lambda 2. To avoid that, what has to be done in place of, for the case of system or system dynamics with pole multiplicity, what the lambda values are to be taken. Now, lambda 1 can be assumed as lambda, lambda 2 will be lambda minus alpha with alpha tends to 0, and lambda 3 can be a large number to identify the transfer function model with no zeros. When you have a 0 in the transfer function model, then this constraint is not required, lambda 3 can be as it is. So, there is no constraint on lambda 3 as far as using the analytical expressions are concerned. Therefore, I can make use of equation number 17, equation number 18, which are obtained from the condition that the output at the first 0 crossing is equal to 0, that results in equation number 17. Similarly, the output at the second 0 crossing is equal to 0, results in equation number 18. These analytical expressions can be used for our case or the case with a plant with pooled multiplicity, provided the lambdas are chosen in this form. Otherwise, one cannot use, because we have seen the limitation. The limitation is evident when you simply look at the C constant or the C, where it is you are not allowed to use lambda 1 is equal to lambda 2. So, it cannot be when lambda 1 is equal to lambda 2, I cannot use C, and subsequently I cannot use the analytical expressions. So, to use the analytical expressions, please assume lambda 1 to be equal to lambda, lambda 2 to be equal to lambda minus alpha, where alpha tends to 0. With this assumption, it is possible to use the 4 analytical expressions we have derived for identifying the general transfer function model. So, whatever I have taught so far, let me repeat. So, the set of analytical expressions that we have derived so far can be used for identifying a transfer function model of the form G s is equal to k e to the power minus theta s upon T 1 s plus 1 square, provided, again let me repeat, provided lambda 1 is equal to lambda, lambda 2 is equal to lambda minus alpha with the condition alpha tends to 0 is used in the set of analytical expressions. Okay. So, how to find explicit expressions for this case to identify this sort of transfer function model using the same general analytical expressions that we shall see subsequently. Let us go to one case. How can we use the same analytical expressions we have used found earlier for identification of the second order plus date time transfer function model with pole multiplicity? Now, we have found an expression for the negative peak output when the plant is subjected to relay control H. A V is equal to minus plus k times H 1 plus H 2 times R 3 power minus lambda 2 upon lambda 1 minus lambda 2 R 4 times R 4 power lambda 1 upon lambda 1 minus lambda 2 minus H 1, where lambda 3 and lambda 4 are given by equations 31 and 32. So, this is what already we have derived earlier in our earlier lectures. Now, how can we use those conditions to find simpler expressions for A B when effort is made to identify second order plus date time transfer function models with pole multiplicity? Now, I will go in that direction. Now, this R 3 and R 4 can be simplified further when lambda 1 and lambda 2 are substituted by lambda 1 becomes lambda, lambda 2 becomes lambda minus alpha with the condition alpha tends to 0. When this is used, then R 3 and R 4 can be obtained further in simpler form. So, how our R 3 becomes? Now, R 3 is equal to let me use the values here. Again we have seen that lambda 3 is there. So, I have to impose a condition on that also. I know that lambda 3 tends to infinity. When that is so, now R 3 will be obtained in the form of R 3 will be equal to 1 minus e to the power lambda tau upon 1 minus e to the power lambda tau p. Similarly, R 4 becomes 1 minus e to the power lambda minus alpha tau upon 1 minus e to the power lambda minus alpha tau p. Please keep in mind how I am getting this R 3 expression for R 3 and R 4. I am obtaining from here only with the substitution of lambda 1 is equal to lambda, lambda 2 is equal to lambda minus alpha, and lambda 3 tends to infinity. When lambda 3 tends to infinity, how do you get R 3 and R 4? Obviously, simply in the form of, as I have done earlier, lambda 1 by lambda 3 plus 1 times whatever you get. Now, since lambda 3 tends to 0, this becomes 0 and you are simply getting a term or an expression of the form 1 minus e to the power lambda 1 tau upon 1 minus e to the power lambda 1 tau p. Similarly, R 4 becomes 1 minus e to the power lambda 2 tau upon 1 minus e to the power lambda 2 tau p. Now, when I substitute lambda 1 by lambda, lambda 2 by lambda minus alpha, I get R 3 h 1 minus e to the power lambda tau upon 1 minus e to the power lambda tau p, and R 4 h 1 minus e to the power lambda minus alpha tau upon 1 minus e to the power lambda minus alpha tau p. So, I have to take the ratio of the two, allow me to take the ratio of the two. So, when I find a ratio of R 4 upon R 3, how it looks like? Now, R 4 upon R 3 will give us 1 minus e to the power lambda minus alpha tau upon 1 minus e to the power lambda minus alpha tau p into. So, R by R 3, therefore, 1 minus e to the power lambda tau p will go to the numerator and we will have 1 minus e to the power lambda tau in the denominator. Now, I can write this in the form of 1 minus e to the power lambda tau times e to the power minus alpha tau. Similarly, the denominator term will be 1 minus e to the power lambda tau p times e to the power minus alpha tau p, and the rest of the things will remain as it is. So, 1 minus e to the power lambda tau p upon 1 minus e to the power lambda tau. Again, since alpha is a small number, the exponential term, keep in mind e to the power minus alpha tau can be approximated as 1 minus alpha tau, since alpha tends to 0. So, using that I can write the numerator as 1 minus e to the power lambda tau plus, or let me rewrite this in detail, so that we will not skip any in between expression. So, finally, R 4 by R 3 can be written as 1 minus e to the power lambda tau 1 minus alpha tau divided by 1 minus e to the power lambda tau p 1 minus alpha tau p in the denominator, and further we will have the terms 1 minus e to the power lambda tau p upon 1 minus e to the power lambda tau. So, upon expansion, the numerator of this will give us 1 minus e to the power lambda tau plus alpha tau e to the power lambda tau by 1 minus e to the power lambda tau p plus alpha tau p e to the power lambda tau p times 1 minus e to the power lambda tau p upon 1 minus e to the power lambda tau. Now, I will divide the numerator term this by this, that will give me an expression of the form 1 plus alpha tau e to the power lambda tau by 1 minus e to the power lambda tau. What I have done? I have divided this term by this. Similarly, dividing this term by this. So, I have to bring this to the down. So, that way that will enable me to write this as 1 plus alpha tau p e to the power lambda tau p upon 1 minus e to the power lambda tau p. So, I have believed that how I have got this expression you have followed. Now, I have divided this by this and similarly this by this, that results in the expression R 4 by R 3 ratio in the form of 1 plus alpha tau times e to the power lambda tau upon 1 minus e to the power lambda tau in the numerator and 1 plus alpha tau p e to the power lambda tau p upon 1 minus e to the power lambda tau p in the denominator. So, we are getting this in some convenient form. Now, why we are doing so? What is the purpose of getting this R 4 upon R 3 ratio? As you see, this peak amplitude or negative peak amplitude has got R 3 and R 4 expressed in this form, and when I substitute lambda 1 by lambda and lambda 2 by lambda minus alpha, your R 3 and R 4 will be available in the ratio form. That is why I am trying to find. So, let me write correct AV form with the substitutions, proper substitution. Then what will be the expression for AV? Now, the same expression or equation number 30 can be written as AV is equal to minus plus k H 1 plus H 2 with R 3 minus lambda 2. So, minus lambda minus alpha, please keep in mind minus lambda minus alpha upon in the lambda 1 minus lambda 2 is nothing but alpha. What I am trying to do? I am substituting lambda 1 by lambda and lambda 2 by lambda minus alpha. That gives me R 3 to the power minus lambda 2 upon lambda 1 minus lambda 2 as R 3 times minus lambda minus alpha by alpha. Similarly, the next term becomes R 4 alpha by this will be lambda 1 is lambda. So, lambda by alpha. Then we have got minus H 1. So, if you see, if I further expand this one, how I get minus plus k H 1 plus H 2 times this becomes R 3 times R 3 to the power minus lambda by alpha times R 4 to the power lambda by alpha, yes, minus H 1. Okay. So, further it can be written in the form of minus plus k H 1 plus H 2, then R 3 times R 4 by R 3 to the power lambda by alpha minus H 1. That is why I have taken the ratio R 4 upon R 3. Okay. Now, we have got AV expressed in the form of AV has become, so AV has become available in the form of minus plus k h1 plus h2 times R3 with R4 by R3 to the power lambda by alpha minus h1. So, this is what we have got an expression for AV, but we have got R4 by R3, R4 by R3 is equal to 1 plus alpha tau e to the power lambda tau upon 1 minus e to the power lambda tau by 1 plus alpha tau p e to the power lambda tau p upon 1 minus e to the power lambda tau p. So, how to find now R4 upon R3 to the power lambda by tau, because this will be whole to the power lambda by tau. Yes, it is possible to find simpler expression for this R4 upon this will be R3, R4 upon R3 to the power lambda by pi. It is not difficult to find. I will use some identity. How it can be used? We know that e to the power some lambda rho can be written as e to the power alpha rho times yes, e to the power alpha rho times lambda by alpha. Yes. So, I can write this as this one, which is ultimately e to the power alpha rho to the power lambda by rho, and when alpha tends to 0, alpha is a small number, the exponential term e to the power alpha rho can be expanded in the form of 1 plus alpha rho. This is known to us. So, using that now I can write the upper expression as, so limit alpha tends to 0 e to the power lambda rho is equal to 1 plus alpha rho, that is for this term 1 plus alpha rho to the power lambda by alpha. Okay. So, when alpha tends to 0, e to the power lambda rho is equal to 1 plus e to the power rho 1 plus alpha rho to the power lambda by alpha. Keep in mind. So, this very much looks like this expression. You minutely observe, we have already got the powers lambda by rho, lambda by alpha here and here. Now, I have got 1 plus certain thing, 1 plus certain thing. Therefore, it will enable me to write this R4 upon R3 to the power lambda by alpha, or this term in some simpler form. So, that will enable me simply to write the expression now in the form of AVH minus plus k times H1 plus H2, R3 remains as it is. Please see, R3 remains as it is. I am not changing R3. And what is R3? R3 we have written already. R3 is given by this one. R3 is given by this one. What changes we have made? I have got R4 upon R3 to the power lambda by alpha is substituted by these two terms now. Where from you get these two terms? Using this identity. Using this, easily it is possible to get this term R4 upon R3 to the power lambda by alpha h this one. Okay. So, I believe that you have followed how I am using. Please keep in mind, always it is possible to find e to the power lambda rho with the limiting value of alpha tends to 0 as 1 plus alpha rho to the power lambda by alpha. Okay. So, when this is used, so this factor simply can be obtained with the limiting value of limit alpha tends to 0, this much becomes this gives us, when I put alpha tends to 0, you see alphas are there, alpha is here, therefore, this becomes your simply nothing but or e to the power this. So, it will give us this ratio will be lambda tau e to the power lambda tau, then again e to the power lambda tau upon 1 minus e to the power lambda tau. This is what you will get for the numerator part, and for the denominator it will be simply e to the power whole of this one e to the power lambda tau p e to the power lambda tau p upon 1 minus e to the power lambda tau p. So, limit alpha tends to 0 r 4 upon r 3 to the power lambda by alpha becomes e to the power lambda tau e to the power lambda tau by 1 minus e to the power lambda tau upon e to the power lambda tau p e to the power lambda tau p upon 1 minus e to the power lambda tau p, and that is what we have got in this expression. So, this the final expression has been obtained from the analysis with the assumption that lambda 1 is equal to lambda, lambda 2 equal to lambda minus alpha with the condition alpha tends to 0 and lambda 3 it tends to infinity. So, when I use all these conditions, the general expressions result in simplified expressions which can further be used to identify the model parameters of a second order model with pole multiplicity, which has got 3 unknowns given as k, theta and t 1. This is how second order plus date time transfer function models with pole multiplicity are obtained using the same set of analytical expressions with the conditions that lambda 1 equal to lambda, lambda 2 equal to lambda minus alpha with alpha tends to 0 and lambda 3 tends to infinity. Let me summarize my lecture. So, the general expressions we have found earlier for identifying the transfer function model parameters of the general second order plus date time transfer functions can be extended for models with pole multiplicity. So, the model can have n number of poles also, it does not matter, the same set of analytical expressions can be used with proper limiting values only, where I can have n number of poles located at the same point in the S plane. Okay. Only thing I have to take care of the lambdas. So, lambda 1 has to be lambda, lambda 2 has to be lambda minus alpha and so on, and lambda 3 can be constant or may not be constant depending on the type of model. Now, model parameters also can be estimated using the 4 measurements. Okay. 4 measurements can be used and the 4 analytical expressions can be simplified to identify transfer function models with pole multiplicity, in which case proper limiting values for different variables are to be used only. The beauty of this is that the same set of powerful analytical expressions, 4 analytical expressions and 4 measurements can be made used to identify a number of plant parameters or process model parameters, where the processes can have pole multiplicity. Now, we will go and to the questions. So, the points to ponder: where second order plus date time model with pole multiplicity. Is it absolutely necessary to find transfer function models with pole multiplicity? Yes, sometimes we have got the system characteristics available in the form of k e to the power minus theta s upon t 1 s plus 1 to the power n. Particularly for poles with critically damped system, for systems with critically damped characteristics, we have got pole multiplicity characteristics behavior given by those systems, and in those case we need to devise or find analytical expressions to estimate the unknown parameters such as k, theta, t1 and n. Therefore, the 4 analytical expressions can conveniently be used to identify the 4 unknowns k, theta, t1 and n with proper limiting values for the lambdas and alphas. Where from you get alpha? This alpha you get with the assumption that lambda 1 equal to lambda, lambda 2 equal to lambda minus alpha. So, some assumption on alpha has to be made as well. Now, any limitation of the identification technique? Obviously, the technique is not free from limitations. One has to make proper use of small number theorem and large number theorems. So, large value theorems or small value theorems, like when lambda 1 equal to lambda, lambda 2 equal to lambda minus alpha with alpha tends to 0, you please do not approximate this lambda 2 as lambda also. It is always lambda 2 equal to lambda minus alpha. Do not substitute alpha by 0 and get lambda minus 0 equal to lambda, lambda 2 equal to lambda. If you use this, then you are not going to get correct expressions. So, care must be taken to find or to apply the limiting theorems, small number and large number theorems properly and accurately to rewrite the general expressions in appropriate form. That is all in this lecture. Thank you.